Hello, so we are the group 4 and this is a presentation of our project for the additive manufacturing course. So let's start by meeting the team. So we're a team of 5 people with Manthila, Beatrice, Paul, Lilian and me, Killian. You're going to be able to see each other in a different part of this presentation. So let's start by speaking a bit more about the project. So for this project, we had different initial ideas, such as cycling helmets, electric guitars, crutches handles, column support for cars or ski boots. So to make the right choice, we decided to do a decision matrix with different criteria. You can read them on the slide. And this decision matrix leads us to the best option, which is the cycling helmets. So why the cycling helmets and what do we want to do with them? So the initial motive of an helmet is to protect the cyclist in case of accident, but in fact, we're sure that it could be way more useful in terms of protection and safety. So the real goal of our new product is to protect the cyclist from other road users. For that, we worked around 2 key points. We want to make it way more stronger with better internal structure thanks to the AM. And we wanted to make it smarter with the use of a lot of technologies, but we're going to speak about it a bit later. So who's going to buy our new helmets? Well, for us, there's 2 main categories. There's the workers who are looking for a more secure and a more comfortable helmet for their daily travel to work. And there are the cycling enthusiasts who are looking for a professional helmet, but at a lower price, because professional ones can be very expensive. So let's speak a bit more about the state of the art and the actual product. So actual helmets are made into 2 parts. You got the outer shell with there to be against impacts and perforations, and you got the inner shell with there to absorb shock energy. You can find helmets at a huge price range, from £30 to almost £500. There's some key elements that could explain this pricing variations, such as materials, weight, ventilation, design, aerodynamics. But in fact, our new helmet is not really in this category for us. It's more into the luxury helmets category. So you can find the XR. This is an existing 3D printed helmet. So where you have a custom honeycomb structure inside, adapted to your head, and a non-3D printed shell on the outside. So this product is actually at £300. And you got also some smart helmets, such as the Unit 1, with at more than £700. This is a small helmet with tone signals, crash sensors, and a lot of different sensors too. And in fact, our new product is quite a mix of these 2 last, with 100% 3D printed structure and shell, and a lot of sensors, tone signals, and GPS inside.
Bicycle helmet standards in the UK. The Bicycle Helmet Safety Standard of the UK is based on a European nation standard that was last updated in 2012. Requirements and testing methods. The safety standard covers multiple areas such as materials, construction and shock absorbing properties that we considered when creating our design, and we will briefly go over it. So, materials. For the materials that the helmet is made of, important requirements are that the material shall not react with sweat or toiletries like deodorant, perfumes or makeup. Next to that, the material shall not cause any skin disorders. Construction. A helmet is made and worn for safety and protection. Therefore, the construction must be able to absorb impacts and stay on the head during an accident. Also, shouldn't injure the user during usage and have a low weight while containing strength. The durability of the helmet is tested with durability tests, where there is made use of test anvils to mimic a fall or accident where the head hits the ground or a curb. Next to that, the helmet is tested for several impact velocities and energies, which it must be able to withstand. The chin strap strength of the helmet is being tested as well, to make sure that the helmet stays on the head during an accident.
The helmet production process begins with an in-store consultation. We have an extensive range of customized options to choose from. Customers can influence the aesthetic design of their helmets and select which smart sensors will be most beneficial for their everyday needs. We have a range of pre-designed helmet styles and colors for selection, and there is also the opportunity for customers to have their own creative input. Customers choose from pre-designed helmet shapes that meet safety criteria, and then select their aesthetic modifications, which include a real photo, original artwork, or customized patterns from existing in-store templates. All designs are printed and adhered to the helmet, ensuring a seamless finish. As the helmet is printed in two parts, you can design different outer shells and rotate between your favorite designs by clipping them into place. There are a range of sensors available based on customer requirements. Additionally, Heaum is committed to innovation. We seek customer input for sensor development. As each helmet is unique, we can take input for individual products. This keeps our helmets adaptable and responsive to emerging user requirements. To ensure a precise fit, we use a head scanning technology based on the Perfect Fit system. This non-invasive process does not require customers to sit perfectly still during the scanning, and accommodations can be made for individuals requiring multiple sessions. A thin, lightweight cap is placed over the head. This gently flattens the hair without applying pressure, and has many small calibration marks printed on it. Scanning software takes around 40 photos to construct an accurate 3D model of the head. This scan, alongside the customer's chosen customizations, ensures the finished helmet produces both comfort and functionality. Traditionally, bike helmets are manufactured using injection molding. While this is ideal for large batches of identical products, it has fewer benefits when considering the level of customization required for this product. Not just so that the helmet is fully molded to the head, but also sensor integration. The correct number and size of sensor mounting points will be different for every helmet. So every helmet will need a separate mold, which is both wasteful, impractical, and expensive. Using an additive manufacturing process enables the level of customization needed to support both a precise fit and integrated sensors. We broadly considered a range of processes before the final selection. These processes were not explored further as they were unsuitable for this application. Powder bed fusion is predominantly used for metal-focused processes. Binder jetting does not produce parts that are strong and durable, and VAT photopolymerization uses UV-cured resins that would not have appropriate shock absorbing capabilities. After researching different processes, selective laser sintering, or SLS, was determined as the most suitable process. We used a decision matrix to determine the best process. The highest weighting was for materials, as an inadequate material, regardless of the manufacturing process, would not make safe helmets. Pre and post processing steps were given the lowest weighting, as all processes will need a degree of pre and post processing and are acceptable for a good finished product. Both material extrusion and material jetting were considered and initially appeared promising due to the possibility of embedding sensors in the helmet during the print. However, due to calibration issues during the printing process and start-stop operations, it is not a feasible solution. Overall, the material extrusion and jetting processes had foreseeable issues with layer adhesion during high-stress applications, as well as the need for supports, which complicates the build and post-processing steps. SLS was chosen and does not experience these issues and will print durable materials suitable for helmets. It also presents a repeatable, cost-effective solution with acceptable production times. It is the optimal choice for high-quality, customized helmets and is the process that has been successfully used by Hexa, an existing 3D printed helmet.
Now we're going to go through some of the considerations we have to keep in mind with SLS. SLS systems can be quite expensive because industrial grade systems usually start at around $100,000 US. But there is a possibility of hiring an SLS facility to print for us, which would be cheaper. In terms of time, SLS is faster than traditional manufacturing methods like injection molding, but it is slower than other forms of additive manufacturing like FDM. Pre-processing for SLS involves adding the polymer powder and preheating the printer, which can take several hours. And then post-processing involves letting the printer cool down, which can take another several hours. and then the excess powder in the bed has to be removed, and the part itself has to be cleaned to remove any powder stuck to it through fuse blasting and sand blasting. The orientation is important because the edges of the powder bed cool down faster, which can cause areas of the part closest to the edges to warp. So the printing orientation shouldn't align with the loading direction. And because the whole part is suspended in the powder bed and the powder acts as a support, there's no need to print any physical supports. To save time and energy, it's possible to nest parts, and there are software to do this automatically. The excess powder can be reused, so there's almost no waste, but the powder does degrade after each use, and when the part is cleaned to remove any powder stuck to it, that powder does go to waste. Tolerances are very small, so SLS is great for printing parts with complex geometries, but something to keep in mind with SLS is that the powder dust is hazardous if someone were to breathe it in. So where do we print? The first option is to purchase an SLS printer. We could buy a small desktop printer, for example, the Formlabs Fuse 1, which starts at $30,000 US. And then there are industrial grade printers like the 3D Systems S Pro 60, which starts at $180,000 US, which is very expensive. So here we have a comparison of both desktop printers and industrial printers. The desktop printers are cheaper, like I mentioned earlier. They take up a smaller workspace compared to a large industrial printer, and they are usually more energy efficient and have a lower maintenance compared to an industrial printer. But having an industrial printer does have some benefits over a desktop printer, like being able to print higher volumes of parts and higher quality parts. The other option of where we could print is to hire an SLS printing facility instead of purchasing a printer. For example, we could submit our designs to 3D Print UK in London, and that would cost a little bit less than £50 per helmet. And again, we have a comparison of both options. If we were to purchase our own printer, we would have full control and more flexibility over the process compared to hiring a facility, so we could change the design or tolerances anytime we wanted. Our designs can also stay confidential, and if we were to hire a facility, then we would be risking our IP. But there are some benefits to hiring a facility though, like not needing to invest upfront as we would if we bought a printer and a workspace for it. And the printer we purchase can also become outdated, which isn't a risk if we hire a facility that has their own top-of-the-line technology. So where do we print? As a startup, we've decided to hire a facility in the beginning because we wouldn't have any capital and it's much cheaper. But over time, we would start purchasing desktop printers and eventually an industrial system for our high volume production. Having multiple printers would mean that we have backups in case any of them break down, and having desktop printers also means that we can print in smaller batches if there aren't many orders. Now onto materials. Here we will decide which material we can use to print our helmet. For a standard helmet, there are 4 functional parts. The liner, which is the part that absorbs the impact during an accident. This is traditionally made with EPS using injection molding, and some other materials like polypropylene are also used for higher-end helmets. We'll be printing the liner with SLS and optimize its topology. The shell is the outer casing, and this is usually made with injection molding, and we'll be printing this part with SLS as well. For the strap and the buckle, we'll be using traditional methods. The strap will be made with nylon fibers, and the buckle will be made with injection molded plastic. Now for the material selection, we can eliminate metals completely because we want the helmet to crumble and absorb the impacts rather than transfer the forces to the head. We also eliminated ceramics because they are brittle and they might break from small impacts and damage the user. TPU and TPE are both a bit too flexible for our case, and polypropylene is a bit too ductile. And both nylon 11 and nylon 12 have very similar structural properties, and both are very suitable for printing helmets with. But we decided to go with nylon 11 because it's more sustainable. It's made from castor beans, so it's fully plant-based. And nylon 12 and all of the other materials come from crude oil. So how much would printing a helmet cost in terms of raw material? We can buy 6 kilogram bottles of nylon 11 powder from places like Formlabs, Additive X, and Solid Print 3D for 718 pounds. And we are printing both the helmet liner and the outer shell. So for a standard helmet, it weighs around 300 grams. So using that, we can estimate the cost to be about 36 pounds per helmet in terms of raw material cost.
Post-processing. All the steps after 3D printing. As mentioned before, the helmet can be customized to the consumer's wishes. This can be done by dyeing, painting, or engraving the helmet or making use of stickers, according what the consumer wants. Also, sensors and gadgets are added in this stage. Gadgets. The helmet contains a 48-hour battery and can be charged wirelessly on a standard or at a hook on the wall, whichever the customer prefers. But also, when the customer is not at home or doesn't have the wireless charger within reach, it can be charged with a standard USB-C cable. The helmet contains brake lights and turn lights, so that the user can be visible at all times for other road users. Besides that, the helmet contains bone conduction in the straps so that I can be listening to music, for example. But the helmet can also tell you when it needs to be replaced after, for example, an accident. When it is the case that your helmet needs to be replaced or some parts need to be replaced, the customer can bring the helmet in and any sensor that still works can be reused. Same for the gadgets. Also, the head scan will still be in the personal file of the customer so that it is not necessary to make a new head scan. Only the broken parts will be replaced. This can also be the whole helmet if that is necessary. Sensors that are in the helmet are an accelerometer, Bluetooth to connect the helmet with your phone, and a combination of a shock sensor with emergency dial and GPS, which needs to be connected to your phone so that in case of an emergency, the emergency number can be automatically dialed and your location shared. For the cost. The price range of each sensor and gadget is given in the table, as we do not want to go for the cheapest, but the most expensive ones are also not directly necessary. An estimated price per product is given. In any case, a customer wants one or another gadget or sensor of a higher quality. This is of course possible, and a more expensive one can be chosen. While taking the estimated prices, which will be more commonly used, it will be around a total of £275 for all the gadgets and sensors.
So the main structure is designed using optimized topology to maximize its performance while saving weight and maintaining its same stiffness and strength. Also at the back of the helmet are located the turn signals and the brake light, controlled by some buttons in the handlebar and in the handle brake. And inside the brake light is located a position light so that other users can see our clients during nighttime to increment its security. This light will always be lit during night, and when the brake will be pressed, the brake light will also lit up. In the main structure are located all the sensors to increment the security and have more gadgets inside it, like the velocity sensors, the shock sensors, GPS, emergency call, and also the heart rate. And at the front part of the helmet is located a light or camera mounting integrated into the design, also 3D printed. And then there are the straps where the bone conducting headphones are located, and the wireless charger so that you can handle the helmet for storage while charging the helmet. The helmet consists of four main parts: the upper part or the cover, 3D printed with some smoothing in the post-processing to increment the performance, aerodynamic performance and cooling. This part can be replaced and can be changed aesthetically thanks to some clips, so it can be easily removed in case you want to have other aesthetics or in case it's broken. The main structure is optimized topology design. It's also 3D printed with SLS and is where most of the sensors are located. The straps are traditionally manufactured and is where the bone conduction headphones and the wireless charger is located. And the last part, for this design, a little tolerance is taken into account to have some space between the user's head and the helmet, so that some foam can be located to increment its comfort and to have a stable helmet. And in conclusion, our product is a mixture between two existing products, but that has never been taken into account or mixed together. One part is the 3D printing helmets. This increments performance. You can make new shapes. It can be more personalized and individualized. And with the advantages of smart helmet, by having a more user experience, a better user experience, and having more security and better performance. And for some future steps, we are looking forward to having better properties of our materials, or having some post-processing methods to increment the performance of our product. And also, as it's been said, our first step will be hiring an SLS company, but in a future we would like to buy some desktop printers and industrial printers to print our own products.
The full helmet package is priced at £650, including an initial 30% profit margin. The final cost will depend on the selected customizations. This places our helmet competitively within the market while offering a combination of personalization and advanced features. We believe it has the potential to push the industry forward, and we're excited about the impact it can have. Thank you for listening.